Alrighty, ladies and gentlemen, boys and girls, we have at long last reached the finale of the 2018 AP Calculus AB free response section. Question number 6. It's been a long journey. It's coming to an end. We do see right away that this is a slope field problem, which is not something we have covered yet. So if you have already watched the slope field video done by Miss Rice, then you should be okay here. If you haven't watched it, you should still be okay. We're going to kind of fake our way through it, but it will begin to make more sense the more of these you do. The good news about these problems is that there's really not that many different things that a slope field problem is going to ask you to do. So after you've done a couple of them, or this one, and then I think there's 3 in your homework assignment that Miss Rice will walk you through, you've basically seen it all. So once we get over the mystery of what the heck this thing is, the problems are not that hard, and if anything, we see a slope field problem on your test, you should be stoked, because it should be pretty easy money. Okay, so all that said, this problem gives us a differential equation, a dy dx, where we have an x and a y inside of this differential equation, and so automatically our mind is going to separable differential equation, general solutions, particular solutions, all that. And so in fact, what we're going to do is skip the slope field section for now, and we're going to go down to the bottom. We're going to go from the bottom up, because the bottom part C asks us to do exactly that, is to turn this differential equation into a particular solution given a particular condition. Okay, so let's jump in there, because that's something that we should know how to do. And this is 2018 FRQ number 6. So part A, we're going to start with this differential equation, dy dx equals 1/3 x times y minus 2 squared. Okay, so first thing we need to do is separate our variables. We see x and y on both sides. We want to put the y with our dy, put the dx with our x. So dividing both sides by the y minus 2 squared, we end up with dy over y minus 2 squared. Multiplying both sides by dx, we then get 1/3 x dx. Okay, so we've successfully separated our variables, and now we're going to take antiderivatives on both sides. Integral symbol, integral symbol. Okay. I know that we've just spent a lot of time with the natural log, and it's very tempting to look at this and think that our antiderivative is going to be the ln, but that's a square. Okay. If it was like that, then yeah, all day, every day, we're looking at the natural log. But this is actually just power rule. So let's rewrite it. Or actually, let's start on the right side and just get this done real quick. Over here, we're going to have x squared over 1/6. Yeah, does that check out? Yep, plus c. So that's our derivative, or our antiderivative over there. Over here, let's do a u sub. Even though you guys are hopefully starting to notice that if we do a u sub on a linear thing where the slope of that linear thing is 1, the u sub really doesn't have any effect, but it's a good thing just to practice. So u equals -2, or y minus 2, and so then du is just equal to dy. Okay, so doing our u sub, we end up with the antiderivative of, let's call this u to the -2 du, and then taking the antiderivative of that gives us a u to the -1. And when we pop that down, we need a -1 out front. So negative u to the -1. And all of this is equal to 1/6 x squared plus c. So we'll sub back in for u. and end up with a negative 1 over y minus 2 is equal to 1/6 x squared plus c. This is our general solution to that differential equation. And at this point is where we should solve for c to get for this particular solution. Because if we try to solve for y here and then get c and somehow get it wrong, we lose this point. So let's do this while it's easy. And so the particular point that we were given, the condition was f of 1 is 0. So f of 1 being 0 means that the point 1 comma 0 is on our particular solution, which means we can come down here, plug in a 1 for x and a 0 for y, and then solve for c. So doing that, we get a negative 1 over negative 2 is equal to 1/6 plus c. So subtracting 1/6, these will become positive. We get 1/2. We get 1/2 minus 1/6 is equal to c. And because we're going to be actually plugging this into an equation, don't box this up, because let's actually solve for this. 1/2 is the same as 3/6. 3/6 minus 1/6 is 2/6, which is a lot like 1/3. So 1/3 is c. So our particular solution, we're going to have c equal to 1/3. Let's go back to that. We'll go negative 1 over y minus 2 is equal to 1/6 x squared plus 1/3. Okay, we cannot box this answer up. We need to get y by itself in order to get the points. So, just because fractions, everybody hates them, let's get rid of them. Let's multiply everything through by 6, which gives us a negative 6 over y minus 2 is equal to x squared plus 2. And already we feel better about our lives. Now what we're going to do is we need to get the y by itself, so we need to get out of the denominator. So we're going to multiply both sides by y minus 2. We can imagine that happening. We have a binomial times a binomial. But then we're going to divide both sides by x squared plus 2. So what's going to look like it happens is we just swap. Okay, we multiply and then divide. We end up with negative 6 over x squared plus 2 is equal to y minus 2. And then we just rearrange a little bit to get that our specific particular solution is y equals 2 minus 6 over x squared plus 2. So that is our particular solution to that differential equation. Okay, part C was 5 points. Okay, so more than half of our points on this question 6 go to part C. So even if we didn't have any idea what slope fields were, we could have gotten more than half credit on this. So the 5 points specifically went to, you got 1 point for just separating the variables. Okay, so for this step right here, showing that we separate the variables, you got an all or nothing 2 points, for getting the two antiderivatives correctly. So the 1/6 x squared and the negative 1 over y minus 2. You got a 4th point for the correct value of c, and then you got a 5th point for the entire correct particular solution. 5 points in the back. Okay, so that was part A. Working backwards still, we're going to go to part B. It says let y equal f of x be the particular solution to the given differential equation with initial condition f1 equals 0. So we actually just found that. It's not actually going to come into play here though, because it says write an equation for the tangent line. So write an equation for the tangent line, that's one of the things we need, to the graph of y equals f of x at x equals 1. And then use that equation of the tangent line, to approximate f of 0.7. We'll come back to this. First, let's focus on this. If we want the equation of a line, we need two things. We need a slope, and we need a point. Well, we've got the point. F of 1 is 0, so that means 1, 0 is our point. The slope, well, we can get the slope because they gave us the differential equation. So slope we can get from dy dx. Okay, so let's go ahead and do that. B. So looking at dy dx, we want it specifically at x equals 1. And this differential equation is 1/3 x times y minus 2 squared. But this depends on y as well. Okay, well, luckily they give us y. Y is 0 there. So we plug in a 1 for x and a 0 for y, and that'll give us the slope at that point. So 1/3 times 1 times 0 minus 2 squared, which turns into 4/3. So our slope is 4/3, and the equation of our line can use point slope, y minus y1, well, y1 is 0, is equal to m, it's 4/3, x minus x1, which is 1. So there's our line. And then the second part of this is they want us to approximate f of 0.7. Okay, we touched on this like many moons ago, but essentially what we're going to do here is use the fact that close enough to a given point, the tangent line at that point gives a fair approximation of the function values there. Okay, because I don't know, whatever this curve is, or just any old curve, let's say that this is 1, and there's our tangent line at 1, and it's got an equation. We can see that if we're close to 1, like at 0.7, let's say, yeah, there's a discrepancy between where we are on the curve and where we are on the function, or on the tangent line, but it's pretty close. It's at least a decent approximation. And so we can use this tangent line at 1 to do an approximation of a function value that's close to 1, in this case 0.7. So for the second part, we're going to say that f of 0.7 is approximately the value we would get by plugging in 0.7 to this function, or this tangent line. So 4/3 times 0.7 minus 1. And I would say box it up and move on with your life. Okay, so in terms of points, that was a 2-pointer. Oh, I made a little boo-boo here. You need to have brackets around here. Brackets around here. Okay, this was 1 point for, 1 point for the line, 1 point for the approximation. There's 1 and 2. Which brings us to the slope fields. Sounds like a place in like a fantasy novel or something. The slope fields of calculus. Let's figure this out. Okay. A slope field for the given differential equation is shown below. Sketch the curve that passes through the point 0, 2, and sketch the solution curve that passes through the point 1, 0. So what a slope field does is it gives you all the potential forms, kind of the skeletons of curves that can satisfy a given differential, that can satisfy a given derivative. Okay? Now, what we're going to see in a second is that the particular solutions to this differential equation that pass through 1, 0 and 0, 2 look wildly different, which should make you a little bit uneasy because we're used to looking at differentials where it's just based on x, okay? And so, for example, you know, if we have dy dx is equal to, let's keep it easy, 2x, we know that that means our solutions are of the form y equals x squared plus c, where this constant is just going to be a vertical shift of this curve. But every single curve that satisfies this differential is going to look like a parabola. Okay? We're going to see in a second that's not the case here, and it's because of this nature of our derivative that is based both on x and y. Okay? So, the actual thing we're doing here is pretty simple. We're going to sketch the solution that passes through 0 or 1, 0, which they've actually labeled for us. And all we do is we start from that point and we kind of just follow the curves. Okay? Each of these things, little dashes, represents the slope of our curve at that point. So this is the slope of the curve at 1, 0. And so we can kind of just trace out along those curves in both directions. Now, one thing that the AP specifies directly is that when you draw this curve, it's got to go to the boundary. So don't shortchange and end here. You don't get the point unless you go all the way there. Now, the solution that goes through 0, 2, we start here, all those slopes look pretty horizontal. So that is a second solution to that differential, which again is not in any way the same as something like this, where we'd expect all of our curves, that are solutions, to be parabolas. Here we've got a line, here we've got, Lord knows what, well, we do know what it is, because this is the solution that we solved for in part C, which is like the rational looking deal. Okay, so just to convince you, or try to convince you that this is a solution, and the particular solution, I'm going to show you on our calculator. There's not a calculator section, so you wouldn't be able to do this on your own, but just to kind of show what I'm talking about. This is the particular solution to this differential that passes through 1, 0. Well, we solved for that in part, I'm sorry, I labeled this wrong. Somebody's probably been screaming at their computer for the past 20 minutes that I called this A when really this is C. And I called this B, well that's actually B, so that reversal worked out. But this guy right here is our particular solution that passes through 1, 0. So let's go ahead and put that into our calculator. We get 2 minus 6 diviso x squared plus 2, close parentheses, close parentheses. Let's use a similar window as we see on the slope field. It looks like it goes from like 2.5. So let's go window x min negative 2.5, x max 2.5, y min negative 2.5, positive 2.5, and turn off my light, okay, and graph. Whoa, okay, so like that makes us feel slightly better that, yeah, okay, we did that part, okay. But then the question is, how the heck is this curve a solution to this differential and the line y equals 2? Because that's what this is. This line right here is y equals 2. And what we're claiming is that this differential equation perfectly describes its derivative. let's see if that holds up to the light of day. Okay, so if y equals 2, is it in fact true that dy dx is equal to 1/3 x times y minus 2 squared? Because that is what we're claiming. And our kind of instinctual answer is heck no, that's like way more complicated than our derivative. Because our derivative based on that equation, dy dx of that guy is 0. 0, 0, 0, forever and always. Okay? Because the slope of this horizontal line is always 0. Well, let's take a little bit of a closer look here. Is it true for this particular solution that this will always be 0? Because if it is, then that satisfies this differential. So the question is this equal to 1/3 x times y minus 2 squared? Well, for this solution, yeah, because let's consider, no matter what x value we have on this horizontal line, whether it's -3 or 17 or 18/3, you can plug whatever you want in for x. Because we're on the line y equals 2, our y value is always 2. Well, 2 minus 2 is always 0. It don't matter what x is, wherever we're at, this does in fact describe our derivative, because it's always going to spit out a 0 on this curve. Okay? And so it's a little bit unsettling that our particular solutions can look so different, because we're used to situations like this where they're different just by a factor of a shift. These are fundamentally different functions, and yet their derivatives in some sort of contrived way follow a similar, or not similar, the exact same rule. Okay, so that's a little bit of a mind crunch for sure, but the more we get comfortable around these problems, I think the easier that'll be to see. So this was our first slope field question. If you're feeling overwhelmed, that's okay. Go watch the notes on slope fields. You'll get walked through 3 more FRQ questions on slope fields, and by the time you finish watching that, I promise you, you will feel like it's no big deal. Okay, so that finishes up the 2018 free response section. It's been a journey. Thank you for sticking it out, and that does conclude my video walkthroughs of the FRQ. So after this, we're gonna have you spread your wings and fly a little bit and try this on your own. Okay, you guys will be great. All right, see you on the other side.